This is a quick glance at the theory of Lebesgue major. Lebesgue major was introduced by Henri Lebesgue in the early 20th century. Henri Lebesgue was a French mathematician that introduced Lebesgue major, which is an extension of Riemann integration. Now, what do we simply understand by the theory of Lebesgue major? Lebesgue major, or the theory of Lebesgue major, is a fundamental concept in modern analysis, particularly in integration and probability theory. It extends the concept of length, area, and volume to a more complex set than those handled by Riemann methods. So that is what the theory of Lebesgue theory stands on. Actually, it's a fundamental concept in the modern analysis that deals majorly in integration and probability theory, which extends the concept of, we talk of a two-dimensional shape. If you want to find the length, or you want to find the perimeter or whatever, you measure is usually the length, that is one dimension. If it is area, it becomes two dimension. For example, so you have this is a rectangle. If you want to find the area of this, you use what? The length and the breadth. Okay? And then if it were, a kind of, let's say that three, dimensional objects, we're talking about the length, the breadth, and the height. That becomes a volume. So the theory of Lebesgue major extends the length, it extends the area, it extends the volume to a more complex set, which is more, in study than the traditional Riemann methods. Now, the theory of Lebesgue at its core introduces the Lebesgue major, which assigns a non-negative number to subsets of real numbers representing their size. That is, this theory assigns, it gives a non-negative a size to every subset of a particular domain. That is, the theory of Lebesgue major at its core introduces Lebesgue major, which assigns a non-negative number to subset of real numbers representing their size. For example, if you say you have a function, just an example, and you have this to be a set x, and this is the real number r, a set of real numbers. So if this is a major, I'm just citing it as an example, but basically we use this symbol to represent a major. If this is a major, of this particular set x, now this major is going to assign a non-negative number. This r could be 0, infinity. If it is extended, this our real number could be 0, infinity. So now every subset of this x will have a non-negative value, and that non-negative value it has is the size of this particular set, because the union of all the subsets of this set will be equal to the set itself. Okay? Now, unlike Riemann integration, which partitions the domains, in Riemann integration, I told you the other time that Lebesgue major is an extension of Riemann integration. So Riemann integration partitions the domain in X like this is now. If it were Riemann integration, it will partition. Can you still remember what I mean by partition? Partition is a set of finite points. For example, now if I have point A and B, so if I want to partition it to finite points, let's say I want to partition it to n points, n intervals. So I will say that let this point be x0. So the next one is x1, followed by x2, followed by x3, followed by x4, and this one would have been x5. Let's write s5 here. So you can see that I've partitioned this interval a, b into how many points, into how many sub-intervals? 1, 2, 3, 4, 5. So we're having 5 sub-intervals, which is our n here is 5. So now, in the case of Riemann integration, that part, one of the concept of Riemann integration actually uses approaches of the approach of partitioning the domain. So in the x-axis, and while Lebesgue integration partitions the range, that is the y. You know, when you say this is the measure now, we call this one what? The domain of a function of the measure mu, while r is called the codomain, where we have our range. Okay, so in Lebesgue integration, the range is partitioned along the y-axis, now allowing it to handle more complex or more irregular functions and sets. That is why that is done in Lebesgue integration. So the key ideas in the Lebesgue theory include: 1, measurable sets. What are measurable sets? These are sets to which a consistent measure can be assigned. So for a set to be measurable, for example, now if I say I have a set, let's call it AI, you know, I can define it. Let me say I have a constant, a real constant r, such that f of x now is greater than that constant. So that will be found in that set. Let's say the major set there is x. So this is a very good example of a measurable set. We could equally have another one which is equivalent to this by saying that alpha is a real constant such that f of x is less than or equal to the alpha. It is still what? Within the domain of the set, and so on. We have about 4 of them equivalent to themselves. So we have a measurable set. We are talking about the key ideas in the Lebesgue theory. We have measurable sets. We have sigma algebras. You know, when we say sigma algebras, it satisfies some axioms that, you know, before you can say a function is sigma algebra, what it must be a collection of sets closed under countable union and complements. So this is also used to define measurable set. These are key areas in Lebesgue theory. We have Lebesgue measure 2, which is the main thing, a function that assigns a size to each measurable set. So if you have a measurable set, Lebesgue measure, this measure now, we assign it will tell you, it will give the impression of the size of each particular measurable set, which form the domain of the function. So which is going to generalize it into the motion of length. Well, for example, now the measure we are talking about is a generalization of length, area, and volume, as we have earlier said. Then we equally have Lebesgue integral. A Lebesgue integral is an integral that is defined using the measure, which is more general and robust than the Riemann integral. I've said this before. Lebesgue integral is more robust. It's an extension. It's a modification. You know, it extends the Riemann integral. While the Riemann integral partitions along the x-axis of the intervals of the domain of the set, the Lebesgue integral actually partitions along the y-axis, talking about the range of the set. And the sets there must be measurable. It must be measurable. So let's quickly look at simple function and step function. This is another core area of Lebesgue measure. What is a simple function? A simple function is defined on a set. You define a simple function on a set, usually a subset of a real number of set of real numbers, and takes finitely many real values, each on a measurable subset of the domain. Now let me give us an example of a simple function. So we have this. This is the generic representation of a simple function. So I can use this. I can use AI. Let me be consistent with A that I've been using here of x. Okay, my I is moving from 1 to n. That's why we say the finite set of is defined on a finite set, and it takes many real values, finitely many real values. So this is a very good representation of a simple function. The function x is coming from the domain of the Lebesgue measure or measurable set, where A is a set of constants, and where this chi AI is an indicator function, or it could also be called the characteristic function. The AI here are sigma algebra, which simply means a collection of subsets of the domain x. Let's say the domain is x. So sigma algebra is a collection of subsets of x. So the phi here is talking about what? The simple function. It's a function acting on the sigma algebra. So if I have this, I can say is this phi taking sigma algebra, which is a collection of subset of x. We have x here, and we have, let's say, r.
So invariably, since AI is a subset of this, so we can have the phi is acting on AI, and whatever element is this phi is acting on will be
set of real numbers. Okay, so that's about that. Now, a step function is defined on an interval of real numbers and is constant on sub intervals. Let's look at a step function.
We have defined a simple function. We now need to look at a step function. Okay, they look alike, but they have differences.
Now, in terms of let's have an example. Let's say that we have this as what the step function. So f of x is equal to ci for each x in the sub interval ai minus 1 ai. So that's the interesting thing about step function. You know, it's a set of constants. Ci and I is moving from 1 to n is defined anyway. It's definite. Let me put it that way. Okay. So this is what a step function. F of x. F is the function. X is the point in the domain, and the domain is usually intervals. So you can see that x is an element within this interval. So x will be and this point ai minus 1 and the ai are the what? They are the endpoints. They are the endpoint. This interval is half open. Because it is open here, it is closed here. So x is a point within the interval. So you can have what? ai minus 1 less than x less than equals to ai. So this f is the what? Is the step function acting on the set of intervals. And the result we are having is a constant. This is a set of constants. So you can see the difference between the step function there and what? And the simple function. So main difference, like I'm just trying to say here, simple function has a finite number of real values. Simple function has what? Because by the time your function, like I said here, the phi acts on this, on the sigma algebra AI, the result will be what? Will be a set of real numbers, set of real values, and they are finite. But in terms of step function, has a finite number of constant value. You can see this is a constant value. Ci is a finite. So we have a finite function of constant value and a finite function of real values. Then another thing about the difference is the domain of simple function are measurable sets, while the domain of step function are intervals. You obviously see the step function here, the domain. So the intervals, like I said here, so this will be what? F taking what? The intervals ai minus 1 ai. So that's the domain going to what? Going to R. So the domain of step functions are intervals, while the domain of simple function are what? They are measurable sets. They are measurable sets. Another thing is that the simple function is used in Lebesgue integration, while step function is used in Riemann integration. I told you in Lebesgue integration we use simple function, but in Riemann integration we use step function. Yes, and don't forget I said Lebesgue integration is extends Riemann integration. It extends Riemann integration. So another thing about their difference is that the structure of simple function is some of scaled indicator function. See, you can see the structure. Chi ai is an indicator function on the what? On the sigma algebra ai. So the structure is a scale. Like this is a linear combination of simple function. That's what we mean by a scaled indicator function. While the structure of step function is a piecewise constant on intervals. This one has what? Piecewise constant on intervals, because you can see that f of x is equals to set of constant function. Set of constant numbers. So it's a piecewise constant on intervals, because the domain of step function is interval. There are intervals, that's the domain. So the result, you can see f of x is equals to ci. So our x is being taken from this half closed interval or half open interval, which is invariably going to be some ci is in half, and so the structure of step function is a piecewise constant on intervals. So with this, we have just looked at the Lebesgue measure at a glance. We have actually defined. We've started with the proponents, that is the scientists that initiated it, and we differentiated between simple and simple and step functions. We've equally defined the concept of Riemann integration and Lebesgue integration. So with this, we have come to the end of this class. So don't forget to click on the notification bell so that each time I upload a video, you'll be daily notified. Thank you.